Welcome to Neural Search Talk interview series by Zeta Alpha. My name is Jakub and today I have with me on the interview Manuel Faysse, who is the author of the recently published ColPali paper, which has caused quite a stir in the information retrieval community online. Yeah, really happy to have you on the show, Manuel.
Thanks. Very happy to be here as well.
So ColPali is a kind of combination of ColBERT and Pali Gemma, right?
Exactly.
But before we dive into what the model does and the results that you achieved in the paper, can you give us and our viewers a little bit of a background on how you came to this project and kind of the story of how you did the research?
Yeah. So thanks a lot for the question. The initial idea is that I'm doing currently a PhD in large language modeling, so NLP, natural language processing, and I'm particularly interested in the information retrieval side. So it's the idea of usually a user has a query and you're going to want to look in dozens or hundreds or even millions of documents to retrieve the relevant documents to be able to answer the user's query. And usually we're doing that a lot on the textual side. So the documents are in text form and the query is in text form. Someone just types words into a keyboard and you get the very relevant documents. So I've been working a lot on this subject. And one of the things that we really kind of see in the industry as a big problem for these sorts of retrieval pipelines is that it's actually very, very difficult to extract texts from documents. Like if you have a PDF document, for example, which is rich in visual information because there's a lot of tables, there's a lot of images, there's a lot of figures, you're going to have to make a lot of choices into how you can extract from these images, from these tables, all of the text, all of the information, and you're going to lose a lot of information. And so nobody really has a very good technique to do this, and a lot of very highly over-engineered pipelines are being built that kind of try to solve this problem, but through complex mechanisms. And what I kind of realized at some point is that nowadays we have a very new family of models called vision language models, which 6-7 months ago could only perhaps describe an image and say a cat is on the image. And about like 4 or 5 months ago, they started becoming better and better, and they started being able to read words off pages that were in the image, or even start to understand documents a bit. And so when I saw this, I realized, okay, it's not anymore just a vision model. It's a model that you can almost do natural language processing with, only having an input on the visual side. And once I kind of understood this, my idea was, okay, I worked a lot on information retrieval on the text side. Can I apply all the techniques I know to doing information retrieval from images directly? And instead of trying to search into text, search from image representation of documents and be able to circumvent all of these complex mechanisms. And so basically, initially I thought, okay, probably it's not going to work. I got to test it a bit and see if it's promising. I tried it a bit. It didn't work so well. I iterated a bit and I got it working very, very quickly. And so at this point, I'm like, okay, so if this really works, we really perhaps got a change in paradigm. There's a new way of doing things, which is going to simplify a lot of things. So let's explore this idea. And we came up with the ColPali paradigm.
So I'm always really interested in how people come to these kind of ideas. So what was for you the aha moment where you thought, I'm onto something here?
I think that, so I work, currently I'm doing a PhD in the academia side, but I'm also funded through a private company, which is called Illuin Technology, which is basically funding my PhD. And they have a lot of these use cases where you're going to want to extract information from tables typically. And there are so many like hours being spent on trying to optimize heuristics, little kind of handwritten functions to extract text from this. And so I've worked a lot on these sort of problems, and it's very, very frustrating. I'm always kind of more into, I think probably with scale, with kind of simple techniques, we can probably go a lot further. And I also like to think of like how technology is going to be in 1 year or two from now. Like I feel nowadays when you're doing AI research, if you focus on solving today's problems, models are just going to get better, and these problems are not going to exist anymore in 2 months, in 3 months. So trying to approach this through like what's going to be something that's going to be unlocked in 3-4 months, and how can we solve it kind of in advance to change the way we see things is kind of how I figured, okay, I think vision language models for document AI is going to be super promising. They started becoming super promising. So let's do something with them, basically. And so I really wanted to work with vision language models for documents.
So your inspiration came kind of from your experience in the industry and building real applications. This is a bit of a wild idea, right? Also, so uh, when did you realize that it would really work?
So I realized it was going to have a chance of working when we started seeing the PaliGemma model came out, basically. And PaliGemma is this vision language model. So it's basically a vision model in which we pair to a language model, and we teach the language model to, instead of just understanding text, understanding what comes from the vision model and trying to leverage both of these models together to be able to solve certain tasks that require both visual and textual information. And when this model, which was relatively small compared to like the very, very big models that were doing it at the time, it was relatively small, show all these performances, I realized, okay, so document AI through vision language models is something that's going to be doable. So now it's my job to make it work for retrieval applications. And so then it was just, grinding with trying a lot of things, coding during a week in my room and trying to get things to work, and eventually it did. And then it was, let's make it rigorous, let's test it out, let's make it into a scientific paper, let's iterate.
Yeah. And what was the so you said first it didn't work and then you got it to work. What was the obstacle that had to be overcome to make it work?
Yeah, so these models, these vision language models, basically, instead of, if we're trying to convert, so the way these text models really work for information retrieval usually is that you take a paragraph of text and you try to represent it into a high dimensional space, a vector space. And so basically you're going to try to convert text into a sequence of float numbers, basically, perhaps, 2000 float numbers, something like this. And so it's supposed to encode enough information in this single vector to represent what the semantics, what you mean, and be able to search later on and match it to a query. On these, when we try to embed pages, so embed like visual information, visual pages, there's a lot of information, a lot of extra information that you wouldn't get through text alone. So you're going to have, the fonts, the spaces, the document layouts, information about potential images, potential figures, tables. And so there's a lot more information that needs to be compressed through a single vector. And trying to do it through a single vector kind of worked. It was promising, but performances were still below what we could expect from just extracting text and then embedding these texts. And so I had to figure out a way to encode more information into encode a document into more than just a single vector to be able to encode more information, be able to search and have a bit more relevant results. And so I tried a kind of parallel approach where instead of trying to encode everything into a single vector, we try to encode everything into multiple vectors.
Right.
And so for this, I kind of remapped what some people were doing with text, which we'll call like multi-vector approaches, ColBERT models, into
so that's where
its
kind of ColBERT
vision equivalent.
late interaction comes in. Yeah,
exactly. And this kind of unlocked, performance and made me think, okay, this could replace what we have.
All right, so let's step back a little bit, and can you try for people that haven't read the paper to kind of really summarize the main idea and the essence of what you have built with ColPali?
Yeah. So I think to summarize the main idea, I think it's first important to explain how it usually works in the industry. If you have a million PDF documents, how are you going to find the relevant one? Usually the way it works is a rather complex pipeline I was saying at the beginning, where first maybe you want to run optical character recognition on the pages, if it's PDFs that are not native, for example. Then you want to run some cleaning strategies to extract, only the content that interests you and remove the headers, remove the footers. Maybe you want to treat titles a bit differently. You want to treat them as metadata. Then you want to have like specific extraction rules for tables, for figures, images. Perhaps you want to use a bigger model to caption them in order to get like a textual description of them, which you're going to be able to exploit later. And once you have all of this, what you do is usually you chunk several of these paragraphs together for it to be like a certain length. You pass it into a text embedding model, and then you create an embedding, so this vector representation that you put into a vector database. And then all of this you can do offline, so you can pre-compute. And when the user has a query, he types in his query, it matches one of the vectors in the database, which is the closest match, and then you retrieve the page. So all of this is the complex process. And what we have with ColPali is basically replace everything in this complex process by a one-step process. It's just you give the page, like an image of the page, you encode it with a vision model, you get a vector, or you get multiple vectors, and then this is what you put in the vector database. You don't need to extract anything. You don't need to have specific rules to treat tables, figures, etc. You just, in one shot, in one forward pass of the model, you get your vector representations and you're able to match them.
In the visual domain. So this is in the your search index is one in the visual domain, so to say.
Yeah, exactly. You never have to extract text. You do everything in the vision domain. And staying in the vision domain.
How can you query such a database in the language with natural language queries?
Oh, that's okay. That's an interesting question. Well, the big advantage of these vision language models is that basically what you have is that you have a language model which is paired with a vision model, but the language model learns to treat what it sees through the vision models as if it were text tokens. So basically you have a fixed vision model, which is going to create several vectors, which are in the vision space representing what it sees in the image. And you feed these different vectors as if it were text token vectors. So basically, you can imagine that the left hand, so it separates the images into a series of patches. So take a normal image, separates it into like a 16 by 16 grid of patches. And the patch which is on the top left is going to have a vector representation. And this is basically treated as if it was a word, like a text word, by the language model. And so you can feed this 16 by 16 sequence of image tokens and then feed text tokens, normal text tokens afterwards, and as a concatenation of the sequence. And then if the model is trained at understanding both at the same time, it's going to be able to treat these image tokens as if they were text, and you're going to be able to generate. So the big advantage is basically that you're mapping image tokens into the text domain directly. And so once you have then your query, which is in the text format that you can type in normally, you're going to be able to match it directly with a representation of the image, which is already projected into the text dimension. So everything is kind of already on the same level, in the same latent space, in the same places. And this enables you to have very efficient matching.
So what's the impact of that? It seems like this has rather large consequences for how people could potentially build search engines. So what are the main implications of this?
The impact is pretty huge potentially, because simplifying this process hugely and gaining a lot of performance, which is what we see. Like we have, about 10x performance, speed performance gains. We get about 20% better performance and doing this extraction on the benchmark that we kind of set out to evaluate everything. And so having better efficiency, better performance, simpler to maintain pipelines for information retrieval, for document information retrieval, can go a very, very long way. And we see that since we released the model and we released all the architecture, the code, the training data, there's a ton of people, a ton of companies that are very, very interested, because it can simplify their process a lot. It can simplify the timelines in which you can start a new document retrieving project and start to use it. And it can take into account information that was not possible to take into account before. All of these complex figures, all of these diagrams that you would never be able to present in text format are now queryable, and so that unlocks a ton of applications.
Yeah, so you can eliminate this whole engineering complexity of the pre-processing pipeline, but it also has, I think, huge implications on the quality of the search results, right? You can ask different questions, and you can get much higher. I think in your paper you show that you actually achieve much higher quality on question answering type of
Yeah.
applications. Can you go into
Yeah,
that?
exactly. Yeah, so one of the the creators of the initial ColBERT paper, which is now a MIT professor called Omer Khattab, he kind of summarized it into a tweet when he saw the paper. He's like, it's not often that you get huge gains in both dimensions, both performance, speed, and like accuracy of retrieval. And we really try to go for both. The fact that we're going faster is because it's done in a single step, so it removes a lot of the complexity. It goes very quickly. But the fact that it performs better is because we're trying to stay in the visual domain. So a lot of the information that will be lost by translating everything, by extracting text, we don't need to do. And this enables us to have, so we evaluated our work through a benchmark which is called ViDoRe. And basically it's a benchmark made of a lot of different academic data sets, but also data sets that we added to be able to have a very rigorous and complete evaluation that matches what will be done in the industry. And we're trying to evaluate a lot of these different techniques, a lot of these kind of industry standard techniques, our techniques, and a lot of the the vision, the vision model
This
techniques
is
that
the main
existed.
table of the paper, right? Where you
Exactly.
evaluate
Yeah.
on this ViDoRe benchmark.
Yeah. And so what we see here is that our technique is able to really outperform a lot of the prior more complex longer techniques by quite a big margin. And this is what is going to shift the paradigm a lot. And what we see maybe on this table, which is interesting, is that there's going to be a lot of documents which are very text rich. So for example, if we look at the column which is shift, so it corresponds to the shift project PDF, so basically very text heavy PDFs on ecological change. We don't see that much of a gap. You see like the standard baseline, which is unstructured with BGEM3, so basically one of the very standard way of extracting text from pages, and then the very, very good embedding models, text embedding models, gets more or less the same performance as what we have with ColPali, which shows that if the document is text only, we are able to match the performance, but there's no visual information to rely on. So it's normal that we don't really get better results. However, as soon as we get into very visually rich documents, such as like archive QA typically, which is going to have a lot of figures. So the first column, there we see a huge gap in performance where we outperform kind of these standard pipelines by about 40%. So our model really shines when there's a lot of visual content to be represented, but it's also super competitive or better when talking about really text-heavy models from the get-go, because there's always even in documents where you wouldn't guess that the layout is important, you still take into account the way the layout, the document layout is structured, the titles, the things like that are things that do make an impact when you want to embed a document for later querying. And so our technique really resembles the way a human will look at a page much more than what a search engine would look at a page traditionally.
So you also show a really big performance gain over clip style models, right?
Yeah.
So I think one of the exactly on this shift benchmark, they are really bad, right? Because they're not actually kind of reading all the words on the page. So can you try to explain a little bit why this Pali-Gemma model is so good at actually reading, like doing kind of OCR, if you want, and really reading all the words and their semantics from the page, in contrast
Yeah.
to something like Clip.
Yeah. So clip or even the initial siglip or models which are really focused towards natural images usually, in which in where we're going to encode images through a transformer, a vision transformer model, and try to get a nice representation from it. What we basically do with ColPali is we take a very good clip-like model. So in our case, we take a siglip model, which is basically a very optimized clip model, and we add on top of this this language modeling component that I explained beforehand, which is going to take the image representation, and we are able to leverage all the prior training of the text model from the get-go. And this is kind of really what changes the game, basically. It's that since these text models are very good, have been trained on trillions of tokens of text that it's seen, you know, from internet data. It's all, you know, it's the classic, you know, big LLMs that you
Right.
know of. Usually, they know a lot of things. They have a lot of world knowledge. They definitely know how to understand, you know, documents, have like reasoning capabilities. And so once you add this to a classic vision model, it's going to be a lot easier for these models to understand the content and the semantics of what it's seeing on the image. And this is what unlocks performance a lot. You know, it's not just seeing letters individually, it's understanding words, it's understanding what's going on, it's being able to read, basically. And this is what changes the game a lot.
Yeah. And so you had the PaliGemma model, and you got it to work as a retrieval model, right? So kind of building these embeddings in the ColBERT late interaction style. So what kind of training did you have to do on the model to actually make that work well?
So to do this, first we had to curate large data sets. Basically, what we really are aiming for is to be able to match queries to relevant documents. And to do this, we used a lot of synthetic data. So basically, we take, you know, PDF documents, and we're going to use vision language models or external, you know, proprietary vision language models that had very good performance, and basically ask them like, okay, look at this page. Are there any queries that might be relevant to ask and that could be answered with information that's present on this page? And so we iterate through this process, and we try to annotate hundreds of thousands of pages with this process. And this basically creates pairs of query to corresponding, you know, positive documents. And using these pairs, what we're like, the training objective is always a bit the same as what we're doing in the, you know, the normal text retrieval community. Is we're going to try to align the representation of the text model. So we're going to try to align, you know, these text vectors, these query vectors, to the representation of the document vectors. So when they're positive, we want them to match and to be very close in the latent space. And on the contrary, when they're, you know, not matching, so when it's a query with a different document, we want them to be as far as possible, like as far away as possible. And so these training objectives are basically contrastive objectives. We put together things that are similar. We try to spread out things that are not. And if you do this sufficiently long, basically, you're going to learn to align everything
you
and
do
create
that,
search
you do
system.
that end to end across the ColBERT, the ColBERT integration, late interaction objective function.
Yes. Yeah, so what I was explaining here is very general. It could work with either, you know, by encoder, so without the ColBERT multi-vector space. When you add, you know, this multi-vector technique, basically it's instead of matching, you know, single vector to single vector and putting them in the space, you're trying to match multiple vectors to multiple vectors through a special operation called late interaction. And the main point of late interaction is to be able to, you know, aggregate a lot more, you know, rich information together, but keep all the performance like the performance interest of these bi-encoder models. So you want it to be very quick, a very quick operation to do, but you want it to carry more information. And so we're able to train everything end to end. We're able to optimize this, you know, in a way that, you know, we can run, and the training goes very quickly. Actually, it's only 8 hours long, and basically we're pushing it a bit. You know, we could make it smaller. So we're leveraging, you know, these very good pre-trained language models, just teaching them to create representations that are a bit aligned with the queries. And once we do that, you know, the trick is done, and we're very happy about how it turns out.
Yeah. So if you so one of the ColBERT is of course very fast and also gives very high quality search results. We actually interviewed Omar Khattab in a recent edition of this Neural Search Talks series. And one of the sort of downsides of ColBERT is that you end up with a lot of representations for each document, right? You basically have a single embedding per word in the ColBERT classical model, and now you're adding these visual patches. So how much information do you actually need to store in your index to make this work for a single page or a single document?
Yeah, that's a very good question. So Basically, what we're doing is, initially I said typically an image could be split into 16 by 16 patches. And so basically for every single patch, we're going to store a vector. So it depends a bit on the resolution of the image, but in the ColPali model that we do, we're storing 1,000 vectors, about 1,000 vectors for every document. So it's a lot, but there's a few factors that could be taken into account here. First of all, these
like
vectors.
one document in your case is one page, basically, right?
One document in our case is one page. So we're storing about 1,000 vectors per page.
Yep.
But this is the naive way of doing things. There's a lot of things that we do and that that are not necessarily invented by us, that are invented by people from the ColBERT community.
Yeah, like the ColBERT V2 kind of compression technique.
Exactly, that can help a lot. So typically, these vectors are a lot smaller than the ones that you would keep if you're doing single vector stuff. So we're doing it into a dimension 128 instead of the classic 1,000, 2,000. So they're 10 times as small. So we already have a gain of efficiency of about 10. And then what we realized is that you can do a lot of pooling. What's interesting is that when you're embedding images by pages, there's a lot of white space. Most of the information that you see in the page is actually not text, but it's all the little white margins and things like this. Right. And this information is not necessarily super interesting. Furthermore, even information that is not white space is going to be a lot very redundant. So we actually looked a lot into can we pool these representations to keep a lot less? And we found that we basically keep 99% of the performance by only keeping about 25% of the vectors. That's really so there's already things like this which are very interesting. And then there's also, since it came out, people have been playing it with it a lot. And they said that you could quantize these representations. So instead of doing everything in 32 bits, you can actually even do it in binary. So just keeping zeros or one. And so when you take everything end to end, taking 128 dimensional vectors, having them into binary representations and pooling them, you basically only, get, you get like a 100x storage decrease compared to our naive implementation, and it goes very quickly, and space is not an issue anymore.
That's very cool. So you would say that a retrieval system on this new paradigm of ColPali, based on only visual patches in the index, could achieve a kind of similar order of magnitude memory size behavior as a traditional index.
So in terms of memory, probably, even though you could probably also quantize, the single vector representations to a certain extent. I think where it kind of differs is in the late interaction operation, where even if you store in terms of memory about the same, you still have to do this late interaction mechanism, which does take which is a compute overhead, and so it's a compute overhead which is almost null if if you're working with 1,000, 10,000 documents. If you're now working with 10 million documents, this becomes a bit different because it's it's a lot of extra compute that you have to go through. And so for these cases, of retrieving in millions of documents, there's kind of extra tricks that we can, use to be able to, first rank all of these documents by relevance using quicker systems, typically, like a bi-encoder style, a single vector mechanism, and then use this, ColPali mechanism to be able to re-rank things with better efficiency, with better accuracy, without losing any of the, the speed gains that we see with other models. So there's a lot, of industry tricks that make it as efficient than other systems, or at least in the same order of magnitude.
So of course, you have these very big relevance and quality gains on very visual style of question answering tasks, like you build the new benchmark for the ViDoRe benchmark. If you look at more traditional information retrieval benchmarks like Beer or MS Marco, I'm not sure if you have done that comparison, but do you still see that what you showed just now in the table, that it kind of at least is on par with the more text based embeddings and hybrid search systems?
The thing is, it's a bit hard to compare because these data sets, like typically MS Marco, which comes from internet text, isn't really associated with any visual information. It's pure text.
Right.
And our method really works, from images.
Yeah.
The way to evaluate them will be to basically just write all of the text on a screen, get a screenshot from the screen, and look at how it's faring. This is something that we actually looked into through Wikipedia articles, basically trying to render Wikipedia articles because it's easy to extract text perfectly from Wikipedia, and we see very similar results. So we see that really passing through the visual domain is not a problem. Having said that, if you have the information already in a textual format from the get-go, I don't think using ColPali is smart necessarily, because you can go with something quicker that also works very well. But I do think, at terms, if we want to unify bits of everything, ColPali is very interesting because humans look through their eyes and read through their eyes. And so it's not only PDF documents, is that you can also, do this with like screenshots of, HTML. So any websites that you want to, reorder, you can do this with diagrams. You can do this with kids drawing. You can do this with basically any form of information that you can represent visually. And as humans, all of the content we produce, we can visualize. And so it's a very generalist technique. So I would say, we try to broaden the scope of what we can retrieve from with this technique.
Thanks. So yeah, very cool work, Manuel. And my prediction is that this will become a classic in the field and really a game changer, and that we will soon see a lot of adoption of this new idea. What are, for you personally and for this line of research, the next steps?
Yeah, so I think now we did kind of the retrieval part. We see that it works very well. But I think, once you retrieve the image of the pages that are interesting to your query, the work is not done. Nowadays, RAG systems are all the rage. Nowadays, you want a language model to synthesize all the information that are retrieved into a nice little paragraph that explains everything, that cites its sources and everything. And I think that's the big main step for this line of work, is not stopping at the retrieval, but doing all of the query answering end to end. And so combining a ColPali-like model with a vision language models that take several pages as an input, like several of the relevant pages that are matched by ColPali as an input, and that is able to synthesize a clear, concise answer with sources and everything, to really have the end-to-end system. And I think this is where you will really have the gains from having retrieving in vision space, never having to extract any of the text, staying in vision space end to end until the final until the final response that a human gets. I think this is going to be a very interesting line of work, and this is what I personally, the team that we're working with, so Tony and Hugues, the two co-first authors of the paper, are working in, but also a lot of people in the industry, a lot of concurrent work. There's a work I should mention, I think, before the interview is over, which is called Document Screenshot Embeddings. And so it's kind of a team that's had the same idea as us, more or less at the same time. I think we both submitted to the same conference, and that are also trying to get vision embeddings through this through the vision space. So I think a lot of people are having the same idea at the same time, and the field is probably going to orient itself towards doing things like this, because it's a lot simpler, it's a lot more scalable, and it works very well.
Yeah, I think that's it's an idea whose time has probably come with the very fast development in large multimodal models, and I think that's the beauty of the style of thinking that you explained in the beginning, that you try to think about where the ball is going to be in 3, 6, 12 months from now, and go there before the other players. So congratulations on this fantastic work, and thank you for the interview, Manuel. So this was Neural Search Talks interview with Manuel Faysse, the author of the ColPali paper. Stay tuned for more Neural Search Talks interviews, and follow us on all the social channels, and check out zeraalpha.com. Thank you.
Thanks a lot, Jakub.